Welcome back, chemistry fans. All right, so what we're going to do is our next topic. It is heat. So we're going to introduce a little bit of that, and then we'll stop, and then we'll pick right back up on the next topic with the formulas. How do we calculate heat? So let's jump right into it. Oh, share. Dink. And okay, so here we go. Sorry about the serenade that you are getting from my son's trumpet. It's just part of the joy of being live recordings. All right, here we go. So what we are going to talk about today is heat and how we can graph it. So what we got to first understand, though, is that all heat is made up of energy. Well, what the heck is energy? Energy is the ability to do work, the ability to move an object from one location to the next. And so essentially what we are doing, as you see in the image, is we are putting effort into an object. We are causing a force to move an object to a new location. Well, that takes moving matter from one position to the next. So that's what it's all about, is being able to move a particle from one place to the next. Well, what are we actually moving, though? This energy. So what we have to do is understand that all energy was founded at the Big Bang. It created galaxies. Inside of galaxies, there's stars. Stars are our sun, and they give off radiant energy. They give off radioactive little tiny particles that are coming towards the Earth. And there are organisms which absorb that, and they use that as the heat, the energy to produce more that animals would eat. Then we eat the animals. We have the energy then to go and move ourselves, do work. And if we are up at the top of a hill, we are then able to transfer that energy into potential energy into kinetic energy. So it's still very vague, I think, in my best opinion, as to what it is, but we do need to take a step forward, though, still. And I think we'll understand a little bit easier whenever we talk about heat specifically. But let's make sure we understand potential energy, energy of position. So if there is a force in the universe, such as gravity, it will act on the body and pull it towards it. And so that becomes kinetic energy. Energy, again, can be heat that we are going to focus on today. It could be movement of particles. It could be simple as sound. Sound is actually energy, nuclear energy, electrical energy, objects moving, mechanical energy. So any of these are forms of energy. What, however, is heat? Well, heat is actually the movement of these tiny particles. So we have been talking about this entire year, atoms and how they're made and how we can measure them. Well, these atoms are actually moving from one location to the next. And as they move from that next location, they then contact other pieces of matter. And so the more they move, the more the energy they have. Well, the more they move, that's more heat. We are actually measuring the amount of movement in the atoms of an object. Now, there's three different ways that these atoms can move. There is convection, which is transfer through the liquid through the movement of the molecules. Conduction, which is the actual touching of the particles, and that's usually directly, so that's a solid one to the next. And then there is radiation, and that's, again, how we get most of the energy here on Earth. And those are tiny little particles that are moving through empty space, or what seems to be empty space, until they hit another object and cause it to move. So we need to understand heat at its essence. It is, again, energy that is moving an object until it hits another object, which detects it. And if we were then moving to the different types of energy, there is endothermic, which is the energy that causes you to absorb it. The object absorbs the heat. Or there is exothermic, you are giving off heat. Here's the interesting thing, though. We always think about endothermic as being hot, you're taking in energy, but the reality is like the ice cube, it could be a cold object that is taking in heat. Versus exothermic, we usually think of those as things that are getting colder. Well, that's not the case with fire. Fire is actually giving off its heat. All right, well, once we understand that, then we have to start putting it on a graph. And we have to then start measuring this heat and how it can change. And what happens as an object heats up too much, it changes its state of matter. The particles continue to move further and further apart. And so the further apart they become, they have less intermolecular force strength. And so they no longer interact with one another. And so we have this graph now that depicts that scenario. We know that there are three states of matter. There is solid, liquid, and gas. For water, we would call that ice, water, and steam. Up here it's listed as gas. And the transition, the flat parts that are on this graph, the first one in blue there, that is where freezing or melting is occurring. And when it is red up here, that's where the boiling and condensing can be occurring. And so we have going up the graph, you are melting, going down, you are freezing, going up the graph, you are boiling, going down the graph, you are condensing. Other terms that could describe boiling would be vaporizing. So you would need to be able to understand that vaporizing means the same thing as boiling. They are just synonyms of one another. Okay, now we can take this graph though, and we could actually reverse the process. It could be going down. And there's no difference in what happens. It's just that this is actually a cooling curve where the other is called a heating curve. But the location of the solid, liquid, and gas are still in the same places as we go through this. One thing I would like for you to pinpoint is as you are going down, the first point of the flat, that is where the condensation point is. It is one exact location. It's not all along this line. Just as this is my freezing point, it is one particular location where that is occurring. Freezing is happening all along, but the first point where something freezes, that is the freezing point. All right, and so again, here is an image where we see these states of matter. They are starting to have perspective. They are losing their interactions. As they heat up, they move faster, they get further apart, and no longer can they be held together. So they start to become a liquid, and subsequently, then they start to become a gas. All right, now, there is a similarly related state of matter curve, and it takes on this Y type of shape that's on the right. We have the heating curve on the left that we just talked about with the staircase plateaus, and this one takes on a shape of a Y. It has three specific regions. You will notice that as we are in the coldest temperatures, we would be at the solid. As we start to heat up, going across here to the right, we would notice that we are increasing in temperature going to the right. That would mean you become a liquid. And as you heat up even further, you become a gas. So on the y-axis is pressure. So we can cause state of matter changes if we also change the pressure. So it's not just about temperature changes. We can change their state of matter. We can cause there to be increases in heat if we change their pressures. If we get the particles closer together, they will give off their heat. If we let them go further apart, they start to heat up. All right, then some specific places on this graph that we need to be aware of. We have our triple point where all three states of matter exist simultaneously on the graph at the same time. So solid, liquid, and gas all occurring at the same time. We also have up here something called the critical point. That is the hottest temperature at which a gas can exist. After we get to this point, we start to have something called a supercritical fluid. And it just means that the gases and the liquids no longer have this distinction betwixt them. They seem to just kind of coexist together. So that's the last time that we have a normal solid liquid gas relationship. Also, we need to be able to discern that the line where there is a difference between solids and liquids, that's where melting and freezing occur. And the line separating the liquids and the gases, that is where we would have boiling or vaporizing and condensing, vaporizing and condensing. Now, the one that we're not familiar with down here is at the bottom, and that's where deposition and sublimation occur. That's the difference between a solid and gas. Much more rare to have that scenario existing. And that's what you see down here on this curve, so, or on these labels here. So melting, freezing, vaporization, condensing, sublimation, deposition. The arrows are indicating which direction the heat is going to cause those. Now, you know, it does actually occur also if we have some pressures that change as well. So just be aware that it's not only temperatures. Sometimes we have it with pressures that can cause the change. The last graph that we must understand is a heat of a reaction. It is this stereotypically shown as this camelback humped graph. It starts high, it goes low, or I will show you the reverse where it starts low and it goes high. And that will determine if you are exothermic or endothermic. There are a few pieces on this graph that we need to be able to understand. The first is activation energy. This is the amount of energy that is required to start the reaction. Sometimes we have to cause friction if we want to get the wood hot enough for it to ignite. The same with a match. You can look at a match and it will never light. You have to add a little bit of friction heat to get the reaction started. Once you get it started, you then have this as your heat of reaction. The difference in the starting point to the ending point, that subtracts that hump up at the top, and it only measures how much difference there is from the starting potential energy to the final potential energy. Because this graph is going chronologically from left to right, we will notice that it is starting high, ending low, meaning it's giving off energy. It is negative. It is giving away energy. So we will call that an exothermic graph. So exothermic would be the graph on the left. It is giving off heat. Endothermic would be the graph on the right where it is taking in heat. If we then notice the last piece of this puzzle is something called the catalyst effect. That is where you see a secondary hump underneath it. And what it represents is the fact that a material has been added and no longer is the activation energy needing to have as much. So you don't have to add as much. So this would be the scenario of you pouring gasoline on wood or on your charcoal starter fluid so that it will actually increase the likelihood that the fire will start at lower temperatures. So what you would see is that in this reaction, what we actually have are particles. They are starting as reactants. They then separate whenever we add the activation energy. They separate and then they come back together to form new bonds over here on the right side. And that's where the products are. And they are more stable. So they are at a lower potential energy. So this is a negative exothermic reaction. All right, this is everything that I wish to share with you today about topic 1. Thank you very much. Talk to you again soon. Bye-bye.